But pretty quickly, somebody came up with an idea of using a two-Poisson mixture for that. Right. So the idea there is what you want is you want to model a distribution which has sort of a heavy head, because most documents are not going to contain the word aardvark. And then you also want to allow for a fairly heavy tail. So that's documents about aardvarks that just keep mentioning aardvark over and over again. You can't get that with one Poisson, but if you combine two Poissons, one that is heavy on the head and one that is heavy on the tail, then you can get the desired property. The idea was to have a mixture of two Poissons, and they conditioned them on a variable. So now you would just call it a prior for the two Poissons, and they at that point they called it eliteness, right? So eliteness is a variable that for a given document is going to dictate whether a word is going to come from the heavy Poisson, from the tail Poisson, or from the head Poisson. And it's just a normal mixture, so you have one Poisson, another Poisson, and you have the two. You have one mixing parameter. So p equals 0 is just 1 minus p equals 1. This model has three parameters. We need the mean for the non-elite Poisson, the mean for the elite Poisson, and the probability of eliteness. And those three parameters you can compute fairly easily using. If you have a big collection of documents and an EM algorithm, for every word, you can figure out what are the two Poissons that describe the frequency of that particular word and what is the appropriate mixing parameter for that. Great. So now you have that, and now you have a distribution that captures a heavy head and it captures a heavy tail, and you can fit it if you've got some data. The problem is this was done not by people who built retrieval models. This was done by people who were doing corpus analysis. Right? And when you want to build retrieval models, what you want to do is you want to take this and say, wait, I also have relevant and non-relevant classes. So I don't just want one of these models. I actually want two of them. I want one of them for the relevant class and one of them for the non-relevant class. And by the way, I don't have any training examples. Right. So, and at that, by the way, the guys who use EM, they just sort of throw a fit and say, okay, go away. So there was some research on trying to make it happen, and Robertson and Spark-Jones, the guys who are actually responsible for the classical probabilistic model, they had a clever idea of conditioning the eliteness variable on the relevance variable in strange and creative ways. The problem is they ended up with a form that had a bit too many parameters and no data to estimate any of those parameters. So in the end, they came up with what they call an approximation. And an approximation is basically you can distill it to the following form. You say that the ratio, so in the context of all of those two Poisson mixtures, remember you have a two Poisson mixture for the relevant class, two Poisson mixture for the non-relevant class, and what they're saying is that ratio, the probability of seeing a particular frequency under the relevant class divided probability of seeing that frequency under the non-relevant class, normalized by the probability of seeing exactly 0 occurrences of the word at the top and at the bottom, that is well approximated by the following formula. And that formula they really did pull out of a hat. Right? So I've looked at it for a while, and there isn't that approximate sign is really a leap of faith. There is no way to derive it. If any of you manage to derive it, eternal glory and respect goes to you. I'm serious. But if you look at it intently enough, you'll actually start recognizing some familiar things there. Right? The right side, we've seen that before, that's just our IDF. Right? And the left side, what you've got there is you've got dW, which is the number of times the W occurred in the document, so that's just the frequency, divided by the frequency plus some big thing that involves document lengths and average document length and some other parameters. So that is none other than our squashed TF that we had on the third lecture as the state-of-the-art TF-IDF ranking formula.